Today I'm going to talk about fab production scheduling, semiconductor fab production scheduling using deep reinforcement learning. Semiconductor manufacturing is one of the most complex manufacturing processes on the planet. It requires a massive scale to build these products at volume at a nanometer scale. It's remarkable that it is even possible at that scale. And this requires a specialized team. So there's a lot of training that needs to occur for people to work in these plants. There's a high level of automations. Nowadays, these big wafers you can't carry around by hand anymore, but the robots actually move it around from equipment to equipment. And there's also a huge investment in these big plants, right? So a plant costs anywhere tens of billions of dollars. Intel invests a lot here in Ohio, and also Micron in Austin. And basically, this is a production process that is almost too complex to really comprehend by human beings. These equipment will run at lower efficiencies than you would like. There's waste involved, and one wafer takes about 3 to 6 months to produce, to come out of the fab. So they actually stay inside the fab for quite a long time. And as we see, there's a big emphasis on nationalizing chip production again. So a lot of experts are needed in the US. So 90,000 experts are needed for nationalizing some of these production processes again. And the production itself requires these very complex machines, often thousands of interconnected machines, where the wafers go in a re-entrant flow. They come back to the same machines over and over again to build up the layers to build these chips. And this process requires to complete millions of steps on these machines per day. And really, that means that just understanding the whole production process that occurs in these fabs is really, really hard to understand, even for the people that have been in this industry for decades. So there's a lot of opportunity for AI to help make sense of how to produce these chips. So that's where our services and product come in, is really to optimize the fab. So how do we go about this, right? So what we do is we combine reinforcement and machine learning together with scalable discrete event simulation. So we use discrete event simulation to model the fab, how the wafers flow from one equipment to another, from lithography to diffusion to etch, etc. Right? And the reinforcement learning agent basically steers these flows in a particular way to optimize certain KPIs of our customers. In addition, often they use lower level scheduling at local stations. So for example, at the lithography tool groups, that is based on mathematical programming, so we have to include that into the simulation as well. So the mathematical programming gives us really good, let's say, robust local decisions, but the reinforcement learning gives us a high-level steering view of the fab. Just to get a little bit of perspective on how we do that, right? So at the fab level, our reinforcement learning agent interprets the fab, sees where the flows are, and steers the lower level schedulers and the dispatching by influencing either their objective function or the set of rules that are currently active. And this is evaluated in a simulation. So the simulation will basically build a Gantt chart about which wafer will go to which machine at which time. And this is the schedule that you can execute in the fab and see if you can optimize the KPIs. So basically reducing cycle time, matching the demands, etc. So the reinforcement learning agent is trained in this simulation and then moved. Basically, the output of the simulation gives the schedule that we execute in the fab. We've had considerable success doing this. Currently, we're deployed in 4 of the most modern fabs of a top semiconductor manufacturer. Their main pain points were basically unoptimized throughput and utilization. They have these, really expensive 250 million EUV litho tool costs. So you want to, optimize that they are used as efficiently as possible. And they also had problems with inefficient response to hot lots, basically lots that have a very high priority that we need to fulfill that demand very quickly. So can we push them through the fab as quickly as possible? And they also had problems with introducing new products because the processes aren't optimized for those products yet. So with our technology, we could have a return of investment that's a 24x per fab, and it is a minimal disruption solution because we basically generate different schedules than the schedules that they are used to, and they can compare the two, and if our schedule is better, they will implement it and run it in the fab. So that helps for the change management of running these 20 billion plus fabs. The types of KPIs that we would improve, right, is things like throughput, that no constraints are violated, that the queues or the work in progress are minimized, and there's little scrap of the wafers, so there's no loss or waste of wafers, and much more. It's often defined by their business objectives. So to give a little bit more sense of how that actually works, I have like a very simplified, well, I would call it demo. Basically, it's how do we switch the setup of certain tool groups dynamically as a function of time. So this is useful, for example, for optimizing the prevention of bottlenecks. So what you can get, for example, in an implant tool group, there can be a bottleneck due to frequent setup changes. And setup changes are basically you have certain products that require a particular mode of operation on your implant tool, and switching from one setup to another setup will take a certain amount of time, so you're taking a hit in terms of the productivity of that tool group. And so we want to minimize the number of setup changes and make sure that there's most of the queues are reduced as well. So our goal is, in this small demonstration, we reduce basically the WIP or the queue length at the implant tool group so that we can improve the cycle time of these products. The baseline which we compare against is a heuristic, a dispatching rule. They generally use dispatching rules for tools in semiconductor fabs nowadays. These are just expert-defined rules based on experience of decades, and they work quite well, but they're local. They only consider what really happens at that particular moment at that tool. So what do? We take this RL agent and we train it to dynamically change the implant setup. So how is the setup at any particular point in time, how it processes these wafers. And it changes the dispatching of which wafers will be processed next. And we do this in a discrete event simulation of a modern fab with a large product mix, including all the common tool groups like lithography, diffusion, implant. All these tools are included. So I'll just give a very simplified view of a fab environment. Of course, this is not what we use in practice, but just to get a little bit of an idea about it. So the observation space of the environment that we have is basically a combination of the queue length of all the tools, the current setup types of all the tools, so in which setups are they now? Are the tools undergoing some kind of maintenance, or are they scheduled for maintenance? Or are they undergoing maintenance at the moment? But usually this observation space or the state of the fab that we take into account is much larger. It's actually a graph of the whole, basically all the wafers that are in the fab plus all the tool states. And this is basically the environment that we take. Then the actions that we will take in this demonstration is basically what fraction of implant tools will we commit to a particular setup. So we basically say in the next hour, you will have to change these implant tools to a particular setup and see if we can optimize basically the queue length at these implant tools. The rewards would then be something like the total waiting time, or it's related to the queue length of the wafers. So we want to reduce those queue lengths. And for this demo, we just use a simple PPO algorithm from Ray RLLib as a demonstration, but generally you would use other algorithms like queue learning or things like this. So here you see some of the results. So on the left side, you see the version that's related to dispatching rules, and on the right side, what the RL agent would do. And you will see basically on the y-axis the different types of tool groups in this simulation. There's many tools. There's hundreds of tools in this simulation. And on the x-axis is basically time, and the color coding is the queue length of at each tool group. And you can see at the implant tool group with the red box, you can see that there's a bottleneck dynamically appearing, while if we let the agent control the fab, the bottleneck doesn't appear, and we basically have less setup changing occurring. The queue lengths are reduced, so it's a much more stable operation state that we're in. And there's also a cycle time improvement related to these products. We also see that this improvement is actually better when we have a higher product mix in the simulation and in the fab, because dispatching rules, they can't really take care of what is happening in the rest of the fab and steer the flows of the products to be at the right time in the right place to mitigate any of these kind of dynamic bottleneck events. In general, this is a very simple demonstration. We take into account much more than these considerations for the fab state. All the different breakdowns of the products at each tool group, the different states that these tools can be in, the reticles related to lithography, the particular constraints of wafer and tool combinations. So there's a lot to take into account, but this gives a little bit of an idea of how we optimize this fab. Now, to give a bit of an idea of how we use Ray, I'll say a little bit about our infrastructure. So we use Ray because it's very easy for us to basically use it on different cloud platforms, so we can easily scale it. These simulations in the cloud, on Azure or Google Cloud, and even deploy on-prem. So a lot of our customers, they don't really like the cloud too much, especially for the production-sensitive parts of our solution. So we definitely need to be able to serve at least the models on their production servers on-prem. And with the Ray stack, it makes it very easy. And we built extra components around it, like algorithms, to help us scale that as well. So which part of Ray do we actually use? Of course, RLLib for the reinforcement learning part, Tune for the hyperparameter optimization, and Serve we use on the production servers to serve the models and make sure that they're safe. We've built around several capabilities around checking these models and providing fallbacks, etc. Also, we built several custom agents and algorithms around this as well. So that's how Ray ties into it. As an interesting side note, what you often get when you're trying to apply AI in real-world cases, you get strange requirements from your customers. And in this case, one of our customers had a Windows-based simulation of their fab. Now, to scale simulations and learn from them, we need thousands or maybe tens of thousands of simulations to be done. We needed to basically make sure that Ray can use Windows VMs and run these simulations and then learn from them. So the reinforcement learning agents can learn from these Windows-based simulations. So we modified the cluster manager, basically built a custom cluster manager to scale up these Windows VMs. As an example, it's just a simple integration of a Windows executable into the environment. So a simulator launch is done via a sub-process that runs that Windows executable. Then the state and reward values are computed based on the input and output files from this simulator and that data is then communicated via the Ray object store to the master process so that the reinforcement learning algorithms can learn from it. This is all compatible with standard RLLib, but we extended it for some options for extra data storage, checkpointing, restoring related to the simulator as well. And also, we need to track our resources, make sure that the memory of these strange Windows VMs are also behaving nicely. So that was basically, on our infrastructure a little bit. Our big vision is really to go towards autonomous fabs. So basically optimize the whole operations of a fab and going even beyond that to the tactical and strategic level within fabs. So we try to optimize basically the schedule generation and all the things that are happening on the operational level to make the wafer flows as best as possible. But then you also have, at the tactical and strategic level, how do we actually plan for the capacity of the fab? How do we match the demand from the customers over a longer horizon? So these are things that we're currently expanding towards as well. And we hope that in the future, fabs will be much more autonomous by themselves, especially combined with AI-driven chip design. We will probably see in the future, in the longer term, that we'll have very dynamic production of custom semiconductor chips going forward. Thank you for your attention. That's it. Any questions?
Yeah.
Go ahead.
I'm curious about how your solution compares to some of the more well-established operations research solutions, I guess. Some of these problems are pretty old, and I'm curious about that comparison.
So it's quite interesting. So if you look at, for example, mathematical programming, it doesn't scale that well with the number of basically wafers. It's usually quadratic. So it works. You can apply mathematical programming, for example, at a lithography machine in a certain formulation, and then it still works quite well. But if you would want to scale it to schedule in one go a whole fab, that's just not possible with mathematical programming. This is also why people use actually dispatching rules, because they're fairly simple. They're very local rule-based decisions. Okay, which wafers will I execute at this particular point in time with the queue that I have. And I think the strength is really where it comes, where we use our RL to take an interpretation of what the fab is doing at any particular point in time, right? And steering these actual lower level solutions that are very good at making local decisions and local optimizations. So that's how I see it, basically.
Any other questions? Well, if there's no other questions, let's give Jasper one more round of applause.